interval observer. I have a state equation of the form xk plus 1 equal to f of xk uk plus a noise, say alpha, and an output yk equal g of xk plus a noise beta. Okay. For this system, which has an input u and an output y, the problem I want to consider is the observer. So what is an observer? An observer is a box represented here, where I have as an input y and u, like this, y and u, and the output of this box is an estimate of the state x at time k. So here it is an observer. A classical observer, the main used by engineers, is a Kalman filter. Here it is not exactly what we want to do, because we have intervals. We measure an interval, so we measure y, but the exact y belongs to an interval, yk, like this, and this one, we know that it belongs to an interval, uk. Okay. And what does the observer? It will provide us a set which encloses the true value for xk, provided that all assumptions on my state equation and the intervals are guaranteed. So it is what we call an interval observer, because everywhere we have intervals, and the CVA algorithm will be used to obtain this set, which will move with respect to time. Okay. It is what is an observer. So to program an observer, I will use some mathematical concept, such as contractor programming, or here I will use separators. Let us recall in few words what is a separator. I have a set, let's say, for instance, a set like this. A separator takes as an input a box, this box, and it will return as an output a smallest box, like this one, which removes only parts of the initial box, which does not intersect the set we want to consider. Okay, so it is the outer contractor, and we also have the notion of inner contractor. So the inner contractor represented here, it only removes part of the initial box, like this one, which all belong to the set we want to characterize. So this set is called X. The blue represents the contractor, the outer contractor, and the red the inner contractor. And the pair of an inner and an outer contractor is a separator. I will start by a simple program, CVA algorithm, which is a branch and bound algorithm, which use an outer contractor here and an inner contractor here. So this is we have a pair of two contractors, which is a separator. To illustrate this, I have a very simple separator, which use the in-ring separator, which is based on a program with using easibex, for instance. We have easibex tool, which makes us possible to build very easily a contractor and thus separators. Okay, so now let us run this algorithm just to show what it is, what we have. The blue has been removed by the outer contractor and the red by the inner contractor, and the bisection has been provided inside the CV algorithm. Okay, so the program is made by a separator, the CV algorithm, which stops as soon as we reach 2000 boxes, which is sufficient. And here we have a simple initialization of vibes to draw boxes, and we draw a simple, very teeny circle, and we call CVA in the main procedure. Another thing I want to introduce to manipulate separators is the notion of transformation. So for state estimation, most of the time we'll need this notion of transformation. So I will explain this now. Assume that you have a system such as x dot belongs to f of x. If you know x at time t, then you can have a function, the flow function phi, which is able to give you the state at time t2. Okay, so here it will be t1 at x2. It will be t1, t2. This is the function. This function phi here is bijective. It means that if you know x at time t2, you can compute x at time t1. This will be the function x of t2, t1. How can we obtain it? So I will try to be simple here. If I have such an equation, I can approximate like this one, x t plus dt is equal to to x at time t plus dt times f of x of t. Okay, so it means that if I can also write x at time t minus dt is equal x at time t minus dt times f of x at time t. So what does that mean? It means that if you know x at time t, so here I will represent the timeline, here is t. If I know, I can compute x at time t plus dt thanks to this formula. And I can also compute I can also compute x at time t minus dt. So if you want, this function corresponds to phi t plus dt. I can go from one direction to another direction. So I can move like this in all directions thanks to the flow function. So, okay, we can guess that when we discretize, k will belong to n, whereas t belongs to r. And we'll have an equation like this one, x k plus 1, which corresponds to this, will be equal to something like a function from x of k. And this function, when it comes from continuous system, like it is the case for in robotics, f, we will know an expression for f, but we will also know an expression for f minus 1. So f will be called here a transformation. Transformation. Okay. So I will now give some very simple example of transformation. If I have here a set, I will be using a set like this one, for instance, an ellipsoid. If I translate it, or if I rotate it, or if I inflate it, and so on, it will be a transformation. So this one corresponds to a rotation, this one to a translation, and this one to an homothétie. So I have shown here only linear transformation, but it can be any other transformation. So why it is important for us? Because if I have, let's say, a separator is a tool to manipulate set. So if I consider here, assume that in my library I have a separator like this one, so associated with this set. For instance, a disk, like this one. And if I want to build from a separator from this, so I will illustrate like this, a separator, for instance, like this, and I will be able to have like this, so a separator, a tool for this. And now what I want to do is I want to build a separator for this set, which can be obtained by a transformation from this one to this one. So I have a transformation, say t or f, whatever. How can I do this? I will first take, so I will illustrate with the outer contractor. I have this, for instance. I will contract it like this. I want to contract it like this, but I don't know how to. I don't have the tool. So first, what will I do? I will move this box here. So it will become like this, something like this, by t minus 1. Then I will contract it thanks to the contractor available for the circle. And then I will move back here by using t. So if you prefer, if I have a set, let's say S, and I have a transformation such as translation, rotation, homothétie, or so what, and I have a set S prime. I have a separator, let's say sigma for S. Then I will have sigma for x prime will be correspond to, first I do t minus, then I use the separator, and then I use t. It is a composition like this, which will be applied to a box X. Okay, so now I will try to illustrate how in this situation, how this can be implemented very easily. I have a separator which makes me possible to obtain this circle, and I want to perform some modification. So I will consider a transformation, and I will program it like this. So recall that for transformation, I need to have an expression, an algorithm for the transformation, but also for its inverse. So I will program here a transformation, very simple. So the transformation, let's call T, takes as an input a box X, and I have an integer A. So what is an integer? Why an integer? Because this integer A equal to 1 if I want to compute T, or minus 1 if I want to compute the reciprocal of T. Okay, so it is a direction of the transformation. Now, what I will take as an example, I will return a box with two components, because in my example, the box will have a dimension 2. So I will return a box with two components. The transformation that we'll consider is the following. It takes as an input x1, x2, and returns as an output 2 x1, x2. It means that if you have as an input this box, you will have as an output this box. So it is clear that on this example, t minus 1 is x1, x2, associate half of x1, x2. Or if you prefer, I can say that t power a, where a is either 1 or minus 1, x1, x2, corresponds to 2 power a, x1, x2. Okay, so I have a single expression for the two direction, for a equal to plus or minus 1. I can have also the same for a rotation. For instance, for a rotation, I will have a rotation of theta power a, or I will just first write like this, will be cos theta minus sin theta, cos theta. Here, if I put a here, a, recall that it is either minus 1 or 1. I can here put a, but the cos it has no effect on the cos. Here I will have a, yeah, I have a single expression for the rotation and its inverse. Okay, so let me come back here. I have my my transformation I want to do. So I return a box. Here it will be power of 2 and a, and here time x of 1, and here x of 2. Okay, so it corresponds to this transformation. If I want now to program this transformation, the rotation, I will call it, for instance, rotate. I will have the angle here, let's say double theta. I write t. Then I will return the box. Cos of t times x of 1 minus a times sin of t times x of 2. This is the first component. And the second component will be minus, so it will be a times sine of t plus cos of time x2. No, I have a problem here. Oh, here also. No, like this. One, it should be okay. Okay, so I have two transformations. And now what I want to do is to move the ring. If I want to apply this transformation, how should I take? How should I do? I will use the forward-backward method, which will be illustrated here. So I take the box A, two components. I will consider also the box B with two components. And recall what I will have to do. Recall here is I want to do this, but I want to combine two transformations. I have the first transformation and the second one, which corresponds to the deformation and the rotation. So I will do A equal to rotate of X. I will take T like this. I have to define T. T will equal to 1 radian, for instance. Rotate -1. Then I will do, let's say, the deformation, T of A -1, always -1 to start, as we have seen before. Then I will contract B with respect to the separator which is available here. And then I come back. So to come back, I will have to do here A equal to T, so it will be the inverse of B in 1, because it is direct. But I have also to intersect with A. This is the principle of the forward-backward method, which is not explained here. And then B, once I have A, so which corresponds, I will have to take X, and X, I take this one. The reciprocal is +1, but I take A here to have the reciprocal. And again, I will intersect with X. Like this. So I will compile it, and normally it should rotate and transform also the initial set. So I run it. There is an error. The error, oops, is poor. I run it. Okay, it starts. Okay. So it is the set. We can see some pessimism here due to the wrapping effect, but we have a deformation of the initial ring and also a rotation. To get a better illustration, I will move t. So t is declared as a global variable. Here I will put t will not be initialized anymore in the separator, but I will do a loop here for the CVA call. So for k equal 0, k smaller than 100, for instance, k plus plus. Here I will change t equal to t plus 0.1, say. Okay, maybe 50. I need also here to clear the figure. Okay, that's all. Let us run this program. There is an error. Okay, here is int. I have to declare it. Compiles, it runs. Okay, you can see it moves with respect to time t. Okay, so we are able to make move the set, and of course it will be inside the, for our observer problem, it will correspond to the set of all state that are consistent with our data. So I will, which problem I will consider for my state estimation problem? I will consider a range-only problem. I will have a mark here, which will be located at 0, 0. And I have one robot which moves. For the simulation, I will know the trajectory. So I will know it will correspond, the position will be corresponds to x1, x2. And it satisfies, this robot satisfies some differential equation, or let's say, we'll have x1, okay, sorry, x1 k plus 1, which will be equal to x1 of k plus the speed p of k times sine of theta of k. It means that if the robot is like this, say, the heading will be theta, and the speed of the robot will be v. Also, we'll have the same for x2, k plus 1. I have to multiply here by dt, okay, x2 of k plus dt times v of k times cos theta of k. So it's a classical model for the robot. What will I measure? For my situation, I will be able to measure this distance. So only this distance, I will call it d of k. And because of this, we call this problem a range-only problem. This is the problem I want to solve here. I will do a simulation. I will remove this. I don't need it anymore. Um, I will keep this. I will draw a circle at the center, which corresponds to the landmark or to the origin. A small circle means, so here it is red, it's the color on the front array, and here it is the color of inside. When I put nothing, such as here, or if I remove this, it means that it will be transparent. We'll see only the border. Okay, so I draw the circle, and I will perform some simulation for double t. So start at 0. I will stop at 5. T equal t plus dt. Of course, I will have to introduce dt as a global variable. I will introduce it because maybe I will use it somewhere also. Then I will take a trajectory. So, of course, this trajectory for the robot x r is equal. So I take an equation, an ellipsoid, t times cos of t, and also for y, I will take yr is equal to, oh, sorry, here it's a plus, let's say sine of t. It is the trajectory of my robot, and of course, this trajectory is not known. I will draw my robot in a very simple way by a circle. So I will put here blue and blue. I will, okay, smaller. There. I will memorize all the trajectory. So to memorize the trajectory, I will declare some global variable because I will need in some other places. So this one I don't need it anymore. I will, so vector of intervals. Because of the uncertainty, I will trajectory will correspond to tube or to vector of intervals. I will have the speed, which is known by my robot. You know its speed. It knows its heading because of some compass, and it knows some distance. So V and theta correspond to the proprioceptive data from the robot, and D is the only exteroceptive data. V is the speed, theta is the heading, and D is the distance to 0, to the mark. Okay. So I put vector because I will memorize all the trajectory. Then I will also memorize, mainly for drawing, the actual trajectory. So for the robot, X robot, Y robot. I will also take as global variable dt, sampling time. For noise, I will consider epsilon. So I will use it later. Small noise, so it will correspond to the noise. And because the noise will be represented by some intervals, epsilon, so with a capital A, corresponds to the interval minus epsilon, epsilon. Okay, so now I will have the number of iteration, Kmax, which will also be used by all my many of my functions. Okay, so let me come back to my simulation here. I will XR dot pushback XR, and also I will do it for Y. So it is the actual trajectory of the robot, which is unknown. I will generate my distance. My distance dot pushback. So I will take the hypotenuse. So I use this function xr by r, which provide me, this provide the distance to zero, to the mark. Plus, I will take a random number. So rand is, I give as an input an interval, x, plus x. So this corresponds to the measurement with a noise. So rand is a noise, but I add the interval because what it means that the data, or maybe I will explain like this, double the distance, d1, which is measured, is the actual distance plus a noise. I take a random number inside with a uniform law. Then I will push back t1 plus the interval minus epsilon plus epsilon, which means that this interval contains the actual data, the actual distance. Okay. Now, once I have this, probably it will draw me. I run it first. There is some errors. Oh, T is not declared, so of course I don't need this anymore. I will not use it. Okay, I will keep it like this. I will not use. Oh, maybe we'll see. Still an error. Okay, it compiles. Whoop, you can see a big circle, but we do not see the trajectory. Okay, probably yes, probably because here it is XR YR. Okay, okay, we see the trajectory. So I start here, I turn left, my robot does this, turns around the zero, and finish the trajectory here. So I will have to compute theta and the speed. I will approximate it. So to do this, I will do a loop for in k equals 0, k smaller than XR, that size. -1, because the last one I will need to compute by the derivative, so I have to stop before. K++. Here it's an approximate. I will compute the speed. Of course, I have to assume here to compute the speed that I know the trajectory, but after I will not use XR and YR anymore. I will use the speed instead. So double the derivative equal divided by dt. It will be XR of K plus 1 minus this one divided by dt. The same here, but with y instead. Then what I will push back? Theta, but push back. Theta push back, so I have to use here the R202 function with two arguments. The first argument will be d by r. Second one will be dxr. So it will be the heading of the robot. Plus I have to add a random number. So random of the interval epsilon. Plus, of course, epsilon. Exactly the same as we have done here, but here we have decomposed into, not here. Okay. I will have to do the same for the speed. V dot pushback, but here instead of we'll have iPod. Okay, so I have generated here all theta and all V, and K max will be equal to the size of V or the size of theta. Okay. Now, what I want for estimation, I will run CVA. I will have something like this for the observer. For K equal 1, K smaller than K max. For all my trajectory, I want to estimate. So I will have to do a CVA of K, and then okay, that's all I have to do. But here there is a for okay. But here, just for debugging, maybe it's better to start with only one. So I will do like this instead. Say that CVA of I will just call CVA of 10. Okay. So this means that I will draw start my my feasible set for the state at time k equal to 10. Okay, so now I will have to come back to CVA and hit k. It will correspond to the discrete time. I am at time k. Here it's time k plus 1, k minus 1, and so on. Okay, so here it will be, let's say, much before. So here it's time k. K minus 1. Another k, so it will be here, let's say k2. K plus 1, and so on. So, in fact, what we will do is for each k, we have a measurement. So the measurement is represented here. It will be an interval measurement. For this interval, I will have all sets that are consistent with this measurement. Okay. But it is, for a range and leave problem, this set will correspond to a ring, and which is not very accurate. What I want to do is to take the previous data into account. In fact, what will be possible? It will be possible to come back here and to come back here at time k2. And for each of these time, I will have also some data with intervals. And from one point here, I am able to come back at time k minus 1, at time k2 in the past, and then to see if I am consistent with the measurement y at time k2, where k2 is in the past in the case of causal observer, or in the future in case of non-causal observer. So here I will more perform a causal observer. Donc, nous on a notre vecteur xk plus 1 qui vaut x à l'instant k plus dt multiplié par v à l'instant k multiplié par, c'était cos θ de k sin θ de k. Donc, ici, on a clairement l'expression de notre fonction phi qui nous permet de passer de k à l'instant k plus 1. Je peux aussi isoler ça. Si je l'isole, je vais obtenir xk est égal à xk plus 1 moins dt multiplié par v de k cos θ de k sin θ de k. Alors, je rappelle que ces quantités sont connues puisqu'on connaît le cap, on connaît la vitesse avec une certaine imprécision. À nouveau, ça c'est la fonction phi qui permet de passer de k plus 1 à k. Mais maintenant, ce qu'on peut remarquer, c'est qu'on s'est passé d'une étape k à l'étape k plus 1. Donc ça veut dire que si ici je représente à nouveau le temps k, on s'est passé de k à k plus 1, donc de k plus 1 à k plus 2, mais on s'est allé aussi en arrière. Donc on va pouvoir développer un algorithme récursif qui nous dit tout simplement, l'algorithme récursif, qui nous dit que phi de k pour aller à k, c'est l'identité. Mais aussi, on va avoir phi de K1, K2. Alors celui-là, c'est pour aller, mettons, K1, mettons qu'il soit là, pour aller à K2, qui est beaucoup plus loin. Alors on a deux cas, si jamais K2 est plus grand que K1, ou K2 est plus petit que K1. Bon, en tout cas, on comprend bien qu'ici, ça va être égal à phi de K2, K-1. Alors ça, c'est plutôt K1, K2 moins 1. Ça, c'est si K2 supérieur à K1. Donc si K2 est supérieur à K1, j'ai intérêt à le faire décroître pour me rapprocher d'une situation où, eh ben, que je connais. Alors ce que je connais, c'est quoi? C'est pour aller de K à K, mais aussi pour aller de K à K plus 1 ou de K à K moins 1. Donc quand il y a un décalage entre les deux, de 1 seulement. Si le décalage est plus grand que 1, ben, je vais me rapprocher avec ici moins de décalage qu'un algorithme récursif. De même, je vais avoir si K2 plus petit que K1, donc si je reviens dans le passé, ce qui sera plus souvent le cas pour moi, phi de K1 virgule K2, ça va être égal à phi. Qu'est-ce que je raconte là? C'est pas exactement ça. Il va falloir le composer. Excusez-moi. Il va falloir. J'ai oublié l'étape de 1 là. Alors ici, il faut que je rajoute plus. Alors, plus que j'ai écrit là, donc les décalages de 1. Donc, plus dt multiplié par U de K2 ou U de K2 où U est défini par ça. Ça m'évite de le réécrire. C'est U. U de K. Bon, je vais le programmer. En tout cas, on a affaire à une transformation qui nous permet de passer de K1 à K2 ou de K2 à K1, mais il va falloir la définir récursivement. C'est là que je vais programmer parce que mes séparateurs, ils vont devoir utiliser cette transformation. Alors, bon, je vais l'écrire ici. Je vais l'appeler la fonction phi. Alors ça, je le supprime. Fonction phi. Phi, bon, l'entrée c'est x. Ici, je vais avoir int k1, int k2. Instant de là où on est et là où on voudrait aller. I will continue in English. Sorry for changing languages. So phi, here, we want to go from K1 to K2, where we are and where we want to go. If K1 equal to K2. So of course I have to return the same box, is identity. Return box of X or return X. Should be the same. Now, if K2 is greater than K1, then I should return phi of x k1 k2 minus 1, as explained before, plus the u of k, the one I have called before u of k, which corresponds to dt v of k2 minus 1 multiply by the box which contains the cos of theta is 1, okay, and the sine. Okay, now otherwise, so it means otherwise it means that if k2 smaller than k1, I should return phi of k1 k2 plus 2 plus 1. So here it's a plus and here it is a minus phi of k2 theta of k2 k2. So here I was copying the expression here. Notice that here I have k plus 1 on the left and k on the right, whereas here I have k and mixture of k and k plus 1. Okay, so since I have copied this, that's why here k and k corresponds here to k2 and k2 also. Whereas here it was k2 minus 1. This is a transformation. I hope there is no problem with the parentheses. It should be okay. So once I have this, I can build my separator. I will have my separators to go as explained here, which corresponds, I am at time k1, I go at time k2, and I want to contract a box, but not with respect to the set of boxes, to the set of points that are consistent with the current measurement, but with the past. So I have to do this transformation to contract with respect to this and come back here. Okay, so that's what I will do now with the separator. So I will have, I will call it observer. Say, okay, K1, K2. Okay, go from K1 to K2. I will box X in K1, in K2, the outer because of the separator, and I will build the forward-backward algorithm. So box A, let's say A of 2. Okay. I will compute A equal to phi of X K1, K2. Then I will contract with respect to the distance, which tells me that S in ring, A of 1, so I will copy this. A of 1, A of 2, the coordinate of the mark 0, 0. The interval here will correspond to the distance that has been measured at time k2, so 2, and here's the outer. And I will come back to the actual time, which tells me that x equal to x intersected by phi, but is to go from k2 to k1. Okay, so probably this one should have been called x at time k2. X, k2, okay, x k2, just to make it more clear. Okay. Now here it is x k2. Now I have to build my other separator because I am here to be consistent. Be consistent with y with the data at time k2, but I do not want to be only consistent with the time k2, but with all time in a window with the past. But I will consider not an infinite window, a small window in the past. Okay. So I will consider here I am at time k. I don't need this. But in this separator, I want to be consistent with the past, but with a past window. So I can take a window of a given length, say of length 5, for instance, with the 5 last data. So I will take a vector, xk, vector of boxes, and I will do a loop to call this separator. Okay. So for in, so k2 will start at k1, k2 should be positive, because before 0 there is no data, and also I have k1 minus k2, which should be smaller than 5. So what I stop my loop, because I want a window of length 5. k2, 1. So because k2 is a past. Start at k1, but I have to decrease it until I go out from my window. What will I do here? I will call this one, of course. So I will do box, I will xk1, which corresponds to x. I will call this separator with xk1, k1, k2. Probably I should have called it k1 here. Okay, k1, k2 with outer, and I will push the result xk, xk1. So I will have a list of boxes or a vector of boxes, all of them being consistent with one data. Then at this level, I have to intersect all of them. In practice, there is some outlier. So either we intersect all of them, so in this case, or we can relax some of them in order to be robust with respect to outliers. So here I will try to be consistent with all of them. And this is my separator. Okay, so I want to consistent with all of them. If if I remove one, it means that I allow one outlier. If I remove two, I allow two outliers, and so on. Okay, so let us try to be simple. It is just an intersection of all xk. Now, this one, I will have to call it here. Okay, and 0. Okay, I start only with k equal to 10. I have some errors. Okay, whoop, 0. Whoop, probably this one. It is the result I obtain. Okay, okay, so there is no inner outer approximation, maybe because of if I put more accuracy, probably I will find something inside than outside, but doesn't matter. Normally we should have. If, okay, I will try. The CVR, I will I run it once more. Oop. Oh, nothing, nothing. Probably because of the state noise. So maybe if we bisect more and more, we'll have nothing. Maybe. Okay, doesn't matter. Something reasonable. And I come back to my loop. But here I will also draw the corresponding circle. Draw circle, uh, green, just to see if I contain or not. Okay. An error. Ah, yes. Here it's XR of K, YR of K. Okay. There is we have to clear the figure. Otherwise, everything is superposed. We do not, no, no, no. Okay, we can see the set here. And even at the beginning, we can see that we have some inner part. Okay, because we have only few data, the frontier is smaller because the state node has not yet appeared, but after there is not anymore inner approximation. Uh, the green point always belong to the set. Okay, so I will stop this. And to have a better visualization, I will remove this one and this one. I will only draw the frontier. I run it. Okay, I have. So we have a superposition. I will see all the trajectory. At the beginning, I can see that at the first step, I only know that I have in this ring, which is huge, but contains the true solution. And here I am at time k. Like at the beginning, you can see that there is some inner boxes that I do not see here, but they are here. And in the first ring, we have some yellow boxes, but we cannot see them here, but they should be yellow. Yes, they are yellow. Yes, it's difficult to, oops, they are yellow. Okay, so it has finished. And we can see that at the beginning, there is some, the set is not, the feasible set is not connected, but after, probably when I am near the mark, the localization is better and I have no ambiguities. Here, it is quite accurate. But of course, after, later, I always contain the true solution. But after, I become less and less accurate. Okay, less and less. Okay, so it is an interval observer that we have programmed here.